to share my screen. Okay, can you see my screen now? Can you see my screen? Can you see my screen? I guess you could not hear me or you could not see my screen.
So you're audible, but and the screen is also visible. But from our end, we are not able to see the icon of muting ourselves or unmuting ourselves.
Oh, so shall I share and share it? So what shall I do?
So
So
we'll try
stop
to join
sharing and
again. So the screen was visible.
yeah. Achha. Now tell me if this is fine, and if you don't see some symbol from your end, you can log out and then join again. So is it fine? Can I start? Is my presentation visible and I am audible? Am I audible?
Yes, sir, you are audible.
And my presentation, can you see slide number 112?
Yes, sir.
Okay, so then proceed. So today we shall start a new chapter. So we finished displacement measurement, which was a very long chapter, and that was very important chapter also. So probably the next important thing is the temperature measurement. So today we shall start a new chapter, which is temperature measurement. So whenever we say the temperature measurement, thermometer and so on. So whenever we say that we want to measure temperature, the quickly one thing will come to your mind, that is a thermometer. And then I asked many questions about the analog thermometer, mercury thermometer, and digital thermometer. And I also derived some expression from where you can see what will be the sensitivity, what may be the resolution, and to increase the sensitivity, what you can do, to increase the resolution, what you can do, how resolution, sensitivity, and all those things are contradictory. One thing you cannot increase indefinitely, that is affecting the other parameters also, other static characteristics. All those things for mercury thermometer is described in detail. So the first instrument which we usually think about the temperature measurement is the liquid thermometer, where there is a liquid bulb, there is a capillary tube, and so. So that is I am not discussing here. This is the first point. Second point is pressure thermometer. So that is also I discussed in first chapter, where you have seen that there is some Bourdon tube and there is some fluid is there, and you have mercury field. You keep that inside the fluid, and then that the liquid increases and it gives pressure, and there is a pointer, and there is a lever and arrangement of scale and pointer, and that pressure elongates the tube, and that pointer gets deflected and you will get reading in the scale. So you have done different parts of it, what is measurement, where is the link, where is the primary sensing element, everything. So that instrument also I am excluding from the discussion because that we have discussed. So the thing I want to start in this chapter is from the thermocouple. Although you know the thermocouple because at class 10 or class 10 plus 2, you read the thermocouple in detail. But maybe few aspect I should discuss because this is also a very important instrument which is heavily used in industry. Okay, that this liquid thermometer is not heavily used in industry. It is used, but this thermocouple is very heavily used. Wherever you will go, either it will be the power generation or the process industry. Everywhere you will see that thermocouple mounted. So, and if you can, you visit any process industry, maybe some petroleum industry or maybe somewhere in TPC power generation. So there you will see that everywhere, starting from the turbine to different piping, this thermocouple is mounted very rigidly and it is fixed. And from there, the data goes to control room, and there the decision is taken, data is recorded, everything is done. So now let's see. So thermocouple is a very important instrument. So let's see the thermocouple. What does it mean? What is the construction? What is the principle of operation of it? Now, if I say the thermocouple, so it means that couple is coming, right? So there are two. So there are two wires. So maybe two wires of different materials. So here you can see that A and B. And if there is a junction, so if you join these two with the help of join means what? You cannot glue the metal, you have to solder it. So if you solder these two, and then you keep the two junctions, so the two junctions are formed. If you keep the two junctions at two different temperature, so there will be some EMF generated which can be measured with the help of voltmeter, that is shown by the E. So thermocouple basically means that the two different metals are joined to form two junctions. That is the meaning of thermocouple. Okay. So there are two thermal junctions. Now we'll read it in detail, its construction. Before that, let's go to the Seebeck effect, which we shall consider because due to the Seebeck effect, this couple works. So what is Seebeck effect? Probably you also know the Seebeck effect. You have read it in your class 11 or class 12. So now let I explain it once more. So let us consider that there is a wire which is made of homogeneous material. Homogeneous material means that material is not changing. Throughout the wire, the material is same. and there is a temperature gradient exists. So what I am saying, suppose we have a single wire and that is made up of homogeneous material and there is a temperature gradient. That means if you say the two end, from the one end temperature slowly changes, and at the another end there is the another temperature, different temperature. So if such thing happens in this condition, an EMF will be produced which is known as the Seebeck EMF. Once again, if there is a wire in which homogeneous made of homogeneous material and there is a temperature gradient exists, so then an EMF will be generated or produced which is known as the Seebeck EMF. Now, how much EMF will be generated, that depends on the material properties, which material you are using, and based on the material, some coefficient which is called the Seebeck coefficient, and based on the material, the coefficient will be different, Seebeck coefficient will be different, and as the Seebeck coefficient is different, the EMF produced will be different for the same temperature gradient. And obviously, if temperature gradient is different, the EMF will be different. That is true. So if you see what I am saying that every metal will show it, this property, that if it is consist of a homogeneous material, I will come if it is not homogeneous material, what will happen. And there is a, if it is homogeneous material, there is a temperature gradient exists. So one EMF will be produced, and the EMF depends on the material property, which is called the absolute Seebeck coefficient. It is mentioned as sigma. So in this slide, you see the sigma, which is a function of T, sigma T. So sigma is called the absolute Seebeck coefficient. Okay. Now, as I assume that it is a homogeneous material, so sigma will be a function of T only. If the material is not homogeneous, okay, if material is not homogeneous, what will happen? Suppose if you have strain to the body and stretching and different thermal stress, all those things. So and due to the material property, then sigma will not be constant. Okay, sigma will be a function of length. So that we are not assuming, and with two homogeneous material, it is easy to take. All the thermocouple is built with homogeneous material. So let us stick to this assumption. So sigma for such material, sigma, which is known as the absolute Seebeck coefficient, depends on the temperature. Depends only on the temperature. So we can write the differential EMF produced dE sigma will be equals to sigma T dt. Okay. So now if we want to know how much EMF will be produced, we need to integrate both the sides. So left hand side will become E sigma and right hand side will become T1 to T2 because the thermal gradient exists and its starting temperature is T1, ending temperature is T2. So we can do T1 to T2 sigma T dt. So if we can perform this integration, that is only possible if you know the sigma as a function of T, we will get that how much EMF will be produced. Okay. So if some EMF will be produced as it is, so you will see there will be some resistance, ordinary resistance R, and then due to the Seebeck EMF, some current will flow, right? So not only EMF will produce, some current will flow inside the in between the circuit consist of the two materials. Okay. So this is all about the absolute Seebeck effect. Will come how it is used in thermocouple. Now before that, see if you have any query. Nobody ask anything, or if you have any query, you can ask. Otherwise, I can proceed. So now with this, now suppose we have two materials, okay, and there are two junctions as I show in this slide. So you see that there are two materials A and B, and there are two junctions T1 and T2. Now if we want to see that much EMF will be produced. So it will be T1 to T2 sigma A dt, that is due to the EMF produced at the metal A, material A, and then T2 to T1 another material, the EMF produced, which is the Seebeck coefficient sigma B dt. So this you can write as the sigma A dt minus, you can change the integration, absolute integration limit, T1 to T2 sigma B dt, and you are getting T1 to T2 sigma A minus sigma B dt, which you can write as a sigma AB. Okay. So sigma AB is known as the relative Seebeck coefficient, which depends on the material both A and B. Okay. So now it is clear. So suppose now we came from the absolute Seebeck effect, we came the thermocouple. So we have two material, we have two junctions. So we can travel to circuit T1 to T2 and T2 to T1, and then we can write it as a T1 to T2 sigma AB dt, where sigma AB is known as the relative Seebeck coefficient. So this relative Seebeck coefficient would be supplied in the form of a table when you are experimenting. So people did experiment with many materials, and then they find out what will be the values of sigma AB for particular two materials when they are joined, and some table is formed, and from there you can see for which two materials the EMF is considerable amount, and those two materials you can choose to build a thermocouple. Okay. Now this is so now up to this point, if it is clear, we will proceed further. So it is clear that so you need some considerable amount of voltage to be produced. So any two arbitrary material, although it will produce a voltage, may not be sufficient. So we did experiment, people did experiment with different materials, and from there, some materials are identified which are used to build the thermocouple. Okay. Even with those identified materials, the output voltage of the thermocouple is very small. So we need to apply a voltage amplifier. So in our lab, we have thermocouple. You used to do experiment. It's very simple experiment. Okay, you put these two junction to different temperature. Generally, we put one junction at the ice, another junction at the room temperature, and then we observe that how much voltage is coming out, and then we keep on changing the another end of the thermocouple and then see how much voltage is coming out. And if the voltage goes through the amplifier, you measure it through the voltmeter, and then you plot a curve, that voltage versus EMF versus that temperature difference. One is always 0 degree in ice. So, and that curve will become the calibration curve. Now, when I give an unknown temperature, you just measure the voltage, you put that voltage on the graph, and then from the graph, you find out what is the temperature of what is the unknown temperature. So that is the experiment. Very simple experiment, and also student did project and they built the thermocouple on their own. And that thermocouple was so good, we did experiment on with that help of on the student made thermocouple. Okay. So it is absolutely simple experiment, and if you do this hands-on experiment, it will be better to see. But I don't know what will happen. The lab component is completely missing, and I heard yesterday meeting that students are enjoying that they are not writing lab report, and there is no point of going to lab. So students are enjoying this life, and next semester maybe also online, as students are in favor of that. They are extremely enjoying this online teaching, and there is no lab report. I don't know, but ultimately my opinion that you people are getting a lot of you are not getting a proper look and proper outlook as well as the proper holistic view of the subject. If you don't do experiment, it might be you might think that it is easy life to you, no need to write the lab report, no need to write come to lab, no need to do this experiment, no need to appear the exam. But ultimately, long run, it is not good. Okay, anyway, so it is about you, whatever you will decide. Now our job is to give lecture, to teach, and your job is not to respond to this lecture, just keep quiet. Okay, that is the life in lockdown, we have to accept. Let's proceed. So what I was telling, that output thermocouple voltage is very small. So we need to have a amplifier circuit there. And apart from that, we need an isothermal block. What is an isothermal block? So to measure the temperature of one end of the junction, another end should measure temperature should be known. So that from delta T, one T is known, another T we could find out. So the common practice is that in lab also we keep such that we use the ice and we keep one end in the ice. Okay. But since ice bath, we call it as a ice bath. So since ice bath is not practical in many industrial application, who will give repeatedly ice, and after sometimes ice will melt, then one person is required to keep the ice always in one bath. So in industry, in lab where the controlled environment is there, it is possible. During experiment you keep it. But in industry, that is not a practical solution, because there are many thermocouples, and for them uh, keeping ice always that is not a good solution. Okay. And further that, if you keep ice and keep on measuring, you will see that the reference junction will not be always at zero, because the temperature will fluctuate. Sometimes it will be 1 degree, sometimes even it can go to 4 degrees, like that. So in industrial application, the keeping the ice is not a good solution. So this ice bath is replaced by an isothermal block. Okay. What is isothermal block? Isothermal block is generally used and can accommodate multiple thermocouples. Suppose you have the many thermocouples nearby, so you keep one isothermal box, isothermal block, and then one another end of the thermocouple you keep the same block. Okay. And using other temperature sensor, you keep measuring the temperature of the isothermal block. Sometimes isothermal block is so designed that its temperature is very precisely maintained with a temperature controller. Okay. So that isothermal block temperature always fixed and it will not change, even the environment condition may change. Okay. So it is so specifically designed that its temperature of the isothermal block will not drift. Okay. So once the isothermal block temperature is known, the isothermal block temperature here it is shown. Isothermal block, you have a measuring junction. You see the ice, you see the thermocouple, you see the voltmeter. Okay. And so if you know the voltage coming out after amplification, so you can divide it by the amplification factor, so you know how much voltage is produced. And from there, one end is on the isothermal block, so you know what is the temperature of the one end. So unknown end, which is exposed to the measuring temperature, can easily be known. So that is the basic principle of operation. Now let's see if you have any query. Okay, till now there is no query. So now next what we will learn, we will see that the law of thermocouples. Okay. So first thing is we read several laws which will be helpful, or if those laws does not exist, then it will be very difficult to build a thermocouple for measuring the temperature. We will see those laws are very, very interesting. And those 6 7 laws, most probably 5 6 laws we'll say. So now two things we assume. First thing is that the material is the homogeneous. So all the materials we are considering here is the homogeneous. Let's say the first law, which is shown as the A, the figure in A. So thermal EMF of a thermocouple with junction temperatures T1 and T2. You see the left hand side of the thing. So you have a two junction temperature T1 and T2 is totally unaffected by the temperature elsewhere in the circuit. Okay, so you see in the left hand side we have two elements, we have two materials which are connected, and junction temperatures are T1 and T2. But other part of the metal, other part of the material, there are T3, T4, T5, T6, there are many temperatures. And those temperature can be different. Suppose we consider the another situation where the two elements are same temperature, T1 and T2 junction temperatures are same, but the temperature in different parts of the junction, different parts of the thermocouple are different, say T7, T8, T9, T10, T11. Whatever be the temperature, it does not affect the EMF until the junction temperature is fixed. So what the first law says? First law says that if a thermocouple are kept in a junction temperature T1 and T2 is totally unaffected by the temperature elsewhere in the circuit. Okay. So this law or rule implies that the lead wires connecting to two junctions may be safely explored to an unknown and varying temperature environment. So if you see this figure, you have one junction, measuring junction, you have another junction, which is the temperature compensated ice bath, and then you have the two chromyl aluminum two material, and they are in the different environment condition, different ambient condition, and that condition is going to change. But those changing condition will not affect the EMF till the two junction temperatures remains fixed. So this law is very important, and this law allows us to safely expose the thermocouple to unknown varying temperature environment without affecting the EMF produced when the two junction temperatures are remains at the same temperature. Okay, means fixed temperature. Okay, is that clear? This is the rule 1. What about rule 2? You come to this B, figure B. Let's say we have a thermocouple where we have the two material A and B. Their junction temperatures are T1 and T2. Now suppose I want to insert another material, okay, C. So in the right hand side of the figure B, you see I want to insert another material of C, right? So right hand side, it consists of the three materials, A, and then C is inserted, then again A, and then B. You note that the junction temperatures T1 and T2 both are at the same temperatures, and also you note that the junction temperature of A and C is T3, C and A is T3. Okay, other part of the C are different, T4, T5. So in both the cases, the EMF produced will be same. Okay, so I'm trying to say in precisely, if a third homogeneous metal C is inserted into either A and B, as long as the two new thermojunctions are at like temperature, the net EMF. So new metal can be inserted as long as the new metal can be inserted as long as the junction. So when you insert the new metal, two more junctions are produced. So if the EMF of the two more junctions which are produced due to the insertion of the new metal are the temperatures of those two junctions are same, T3 and T3, here you see the net EMF of the circuit will be unchanged irrespective of the temperature junction T3 and irrespective of the material C inserted in the circuit. Is it clear? This law makes it possible to insert a voltmeter. Suppose if this law does not exist, EMF difference will be created, but you cannot measure it. How you will measure it? You measure it with a voltmeter. If you want to measure it with a voltmeter, you are inserting a new material and you are creating more junctions. So if that affects the EMF, then you cannot measure. So although it is produced, it cannot be used as a sensor. as these laws or properties says that you can insert a new material and the EMF will be same until if the junction of the new materials are in the same temperature. Here it is T3, so same EMF will be produced. This law, the second law, make it possible to insert a voltage measuring device to measure the voltage rather than only talking about that some voltage is will be generated. Okay, this is a very important law. This gives us the flexibility to use the thermocouple as a sensor or as a temperature measuring device. Now let me see if you have any query or if you want me to tell this thing again. Okay, nobody is telling so everybody understood everything, so let me proceed. Now let's come the third figure. Okay, so this is the rule 3. If a new metal is inserted, here you see a new metal is inserted between the two material A and B at one of the junction temperature. Here it is the T1 temperature, one of the junction, and the temperature of C at any point of the junction, that means at the junction AC and the junction BC, both remain fixed or same as the earlier. Here it is T1, you see T1 and T1, and there may be other temperatures, different part of the C, as long as these two junctions, new junctions, due to the new temperature is remain the same as T1, the same EMF will be produced. Same EMF will be produced. Okay. Again, I am saying if a new material C is inserted between the two material A and B at one junction. So in previous one, we inserted another material C in the middle part, not in the junction. But even if we insert the material C in another one junction, one of the junction, but the temperature of newly two formed junction remain same as T1, and as long as the junction AC and BC are both at the temperature T1, the net EMF will be same as earlier. So this law makes it possible or makes us possible to insert a voltage measuring device at the end or at the junction. This is one point. Second point is this property gives us allow us to solder the junction with the new material. When you solder the junction, suppose you have the two material rod and you want to wire, you want to fix this. Otherwise, if you cannot fix it, you cannot make a junction. Suppose you want to fix it, and how do you fix it? You will make a solder. When you solder it, what will happen? A new metal, that is soldering material, new material will come in between the two material A and B, and that will fix, new material will be fixed in between them. So in that case, you are inserting a new material which is C, and if this law does not exist, you cannot solder. So you cannot make a junction out of the two materials. Okay. Now let's go to the next rule, rule D or rule 4. If the thermal EMF, you see there are three thermocouples we have drawn. One is A and C, one is C and B, and last one is A and B. Here you see if we are making thermocouple with A and C, the thermal EMF will be EAC. If we are making thermocouple with C and B, the thermal EMF will be ECB. And if we are making thermocouple with A and B, C is silent, C, so this will be EAC plus ECB. Okay, so if we tell that if the thermal EMF of metal A and C is EAC and that of metal C and B is ECB, then the thermal EMF of A and B will be EAC plus ECB. Okay, so these laws says that all possible pair of metals need not to be calibrated, since the individual metal can each be paired or standard with paired with the other material which is already calibrated. Okay. So So you don't need to do the experimentation of the material with A and B also. So if you did it with A and C and you did it with C and B, then you can know that how much voltage will come when you keep the metal A and B together. Okay. The last rule, it says that you see that there are two materials A and B. It is forming thermocouple. It is creating E1 voltage when the temperature of the junction is T1 and T2. When you connect the two wire A of A and B and you keep the same material but the junction temperature is different, it is T2 and T3, and there the EMF produced is E2. And when you do the thermocouple, prepare the thermocouple with the two material A and B where the junction temperature is T1 and T3. You see that intermediate T2 is not there. So junction temperature is T1 and T3. And in such cases, the EMF will be E1 plus E2. Okay. So you don't need to think about what will be the EMF. If you have the one junction fixed, you know that T1 and T2, and you know that T2 and T3, and one junction is common temperature, one junction temperature, then the temperature EMF produced due to the junction temperature T1 and T3 will be E1 plus E2. Okay. So whenever you see some thermocouple in circuit, you will see these all five laws you need to apply, and then with the help of all five laws, you can think about that that insertion of voltmeter is possible, insertion of different material is possible. Okay, so all those things is possible. Now, if you see one example that how that thermocouple circuit is built, this is really a nice thing. So if you see that there, so chromel alumel, these two wires are doing the thermocouple, and there is a temperature T measurement. You see that you have to measure. There is some T ambient temperature, and you see there is a isothermal block. What I said, that isothermal block means that block temperature remain fixed by some external means. Okay. So there, this chromel and alumel both are fixed. And then from the isothermal block, copper wire is coming out, and one copper wire is going to voltmeter. Another copper wire can directly go to voltmeter, definitely. But generally what happens, that goes to a compensator circuit. What compensator circuit does, it measures the T reference. Sometimes it measures the T reference and it compensates it. And ultimately from the output voltmeter and measurement and the compensator circuit, you know the how much voltage is produced, and you know the temperature of the isothermal block that is coming from the compensator circuit. You see that the compensator circuit, what is do? Well, it is actually the circuit which produces some temperature when isothermal block temperature remains decreases and when it increases it. So it is basically the temperature controller. So you know the T reference, you know the temperature of isothermal block. So from there you can measure the temperature T measurement. Okay. So that is being done in real practice. Okay. So if there any query, let me see. Okay, there is no query. So let me proceed then. Now in industry, you will see there are many thermocouples are common. That means the thermocouples made of the many materials are common, very common. So, and you need to choose one thermocouple. How do you choose thermocouple? Which thermocouple for your particular application? The first thing you need to choose that what will be the sensitivity. That means if the voltage produced is high, that you need to choose compared to the voltage produced is high. Low. The next thing you need to choose that your temperature range, which temperature range you want to measure. Okay. So if you want to measure very large temperature range, you have to choose accordingly. You have to measure the small temperature range, you have to choose accordingly. And the commonly used thermocouple sensitivity is that I should tell, it is generally 60 microvolt per degree centigrade. Okay. So that means in change in 1 degree centigrade, 60 microvolt will be changed. So now there are various types of thermocouple. So important type is type SR. SR means the thermocouple made up with platinum and platinum rhodium. Okay, you see that platinum and platinum rhodium. Okay, so type S, which is platinum 10% and rhodium platinum rest, is called type S. Type R is platinum 13% and rhodium platinum is rest, that is type R. So if you see that, generally this can measure up to 0 to kind of 1500 degrees centigrade or even more it can measure. Okay, another important thing is chromel alumel. This is very costly as it is made up of platinum. So another cheaper version will be chromel alumel, that is also very popular, and that is called the K type thermocouple, and the range is from minus 200 degrees centigrade to 1300 degrees centigrade. Range is also very good and it is cheap. It can be used in industry. Another thermocouple is the type T, that is um, that is copper constantum. This is also very useful for some application because but its range is quite low. For example, its range is minus 200 degrees centigrade to around 350 degrees centigrade. Okay, so its range is quite low, but it is good. Use sensitivity is good. Okay, it produces lot of voltages. So you can use this if you are measuring within this temperature range. Iron constantum is another, it called the type J. It is also very good, and so it is minus 150 degree to around 1000 degrees centigrade. And chromel constantum, that is called type E, that is also very high sensitive, but its range is less. Okay, so based on the sensitivity and the range and your type of application and you whatever the temperature you want to measure, based on the range of that you need to select the thermocouple. Okay, so these are the very common type of thermocouple which is very popular in industry. Now, if you see the construction, the thermocouples, there are various types of construction. So, few important consideration you need to make before you select that what will be the thermocouple material and what will be the construction. First thing is that thermal EMF versus temperature curve must be always increasing. You should not take any material where it is decreasing after some times, because then it will create a not monotonically non-monotonically increasing, so it will not serve the purpose. And the curve should be as linear as possible and as deep as possible. Why as linear? Linear curve is always useful. And why as steep? Steep means its sensitivity will be high. So it should be linear as possible. It should be as steep as possible. Slope will be high, so generated voltage will be high for the same temperature difference, and it should cover the whole range. Whatever temperature you want to measure, it should cover the whole range. This is the first point of consideration. Next point of consideration is material and type of the scenario where you are using. So it should have very high melting point, so that if you want to measure something and the thermocouple should not melt with the temperature of that, and it should be made with the homogeneous material. So otherwise sigma will not be constant, then it will be very difficult. And it should be made in the desired shape. Okay, most of the time thermocouple is kind of eye shaped. Okay, it's kind of only one probe kind of thing. And another important consideration is it should be resistance of corrosion. Why? Corrosion and mechanical strength. So in process industry, you don't know, there are different types of fluids going. Some fluids are very corrosive. If suppose you have some petroleum industry, you are in some producing some acid or something which is very corrosive, so your thermocouple probe should not be damaged by the corrosive. And another thing is that sometimes the liquid flow rate is very high, and in that case you must have mechanical strength, otherwise with wear and tear it will break easily. Okay, so based on all these consideration, you have to choose the material, you have to choose the shape. There are different types of shape. In this slide I show it. So one time shape, you see that the leftmost, it is the bare wire. That means the that means the two thermocouple wires are bare and they are exposed to the fluid or the environment it want to measure. Next one is bare wire with beaded. There is some bead in the, and another two types, you see that the insulated junction. Insulated junction is required when you want to measure something which is very corrosive or which is very you need some mechanical strength. In that time, that type of scenario, that insulated junction is very very useful. And also sometimes you see the grounded junction, you see that grounded junction. So outermost mid coating thing is grounded, that means connected with the thermocouple, okay, junction. So that is always that is also useful. You see that outermost coating, most probably many of the times it is made of stainless steel, and so that the temperature quickly transmit to the thermocouple, okay. And there are some advantages if you use the bare wire junction. There is some disadvantages if you have the insulated junction. Always you will not directly connect it to it. There is some time, response time, it will need to pass the temperature from stainless steel to thermocouple, okay. Uh, so if the junction is must be grounded sometimes, you see. So these are the different types of, when it is very safe environment and there is no wear and tear, bare junction is good, okay. So that response is very fast compared to the compared to the insulated junction. And uh, and it's also measuring temperature and slowly flowing. If it is non-corrosive gas or liquid, and the flow rate of the gas or liquid which you want to measure is very less, this kind of bare wire is very useful. So you read all those things from the book. In the book everything is mentioned, advantages, disadvantages, all those things, okay. And now let me see if you have any query. Okay, so here we end the thermocouple. So if you have any query on the thermocouple, you can ask. So we have one more class to go, and hopefully rest of the things will complete. So our syllabus will be up to the temperature measurement, and so your Viva will be full syllabus from the starting to the end. End means tomorrow, whatever I teach up to that. And you will read properly, you will give the Viva properly. So it is Friday, Saturday, Sunday, and this is very much useful because it is most important. Up to this point, you have realized that Viva is very important. So it's all about, if you have any query or anything, you can ask. Um, so otherwise, we'll end here. Okay, so you don't have any query and all of you are leaving. So let me stop here. So one more class I will take and then you will appear for the exam. So thank you all of you for attending the classes, although you are silent. So still I give big thank to all of you and have a good day and prepare for the Viva. That's all. Thank you. Now I drop.